Using a standard 2-metre quarter wave ground plane antenna and a VHF radio tuned to 145.8 MHz FM, I recovered a few slow scan television or SSTV images transmitted from the International Space Station. The ISS is transmitting SSTV images this weekend as a celebration of the 35th anniversary of the first amateur radio contact from an orbiting spacecraft, which I believe was the Space Shuttle. Now, this is a great opportunity to test the performance of my equipment for this unique challenge of receiving signals from space. At 12:05 UTC, or 8:05 in the evening local time, the signal triggered the SSTV application almost as soon as the spacecraft breached the horizon. The image is unrecognisably noisy to start and of poor quality throughout the image recovery. The poor quality of the image is due to a couple of reasons, I believe. Initially due to local terrain obstacles at the horizon. Also possibly the ISS antenna, from what I understand, is a simple whip antenna and may be in poor orientation to my aerials, and may also be due to possible ISS obstacles interfering with the signal, for instance solar panels, major parts of the spacecraft, etc. An issue that I had not thought of initially was the spacecraft is heading towards me at more than 28,000 kilometers per hour, or more than 17,000 miles per hour, and this will cause a Doppler effect on the signal, with the signal appearing approximately 3.5 kilohertz higher in frequency. I have the VHF receiver set to wideband FM to hopefully compensate for a Doppler effect. However, the radio may be slightly off frequency, and I think this may be the main reason for the generally degraded image on the first image. The second image is almost perfect. The spacecraft is now passing the closest point to me a little over 500 kilometers. The relative speed is low, so the Doppler effect is not an issue. There was a momentary dip in signal strength, and I'm thinking this may be due to Faraday rotation. Faraday rotation being the rotation of the signal's polarization as it passes through the ionosphere. There may have been a momentary crossing of phase of the signal with my antenna's vertical polarization, causing a large attenuation. In future, this could be reduced or eliminated by using a cross-dipole antenna or similar that are way less phase sensitive. Keen to hear comments on this, if anybody has any further thoughts. The third image starts out perfect, however deteriorates into the noise as the spacecraft approaches the horizon at a distance of over 2,300 kilometres. At 13:44 UTC, or 9:44 in the evening local time, the signal triggers the RX SSTV application well into the second pass. This is the second orbit. The spacecraft is now over 11,000 kilometres at the closest point. Doppler effect would be much less of an issue as the relative approach and departure speed is much less. The fourth image is almost perfect. At 13:46 UTC, or 9:46 in the evening local time, the signal triggers the RX-SSTV application for the fifth image. There is two dips in the signal strength that again I'm thinking is due to Faraday rotation. The second dip was much longer and the same complete null of the signal. The signal is, as has been for most of the image, generally very strong, well over S9. The fifth and last image finished very strong and the spacecraft was still well above the horizon. Okay, all very interesting. The main takeaway from me is that while the ISS signals are relatively strong, the signal polarization is the main issue to be dealt with for otherwise perfect image recovery. Again, a multi-polarized antenna such as the cross dipole or one of the other antenna types commonly used for NOAA weather satellite image recovery systems is definitely required for better SSTV from low orbiting spacecraft and general signal reception. Alright, keen to hear comments on this. Thank you for watching.